talking about is that this is the PhD thesis work. And this is the second paper of the PhD thesis of our student Nagamani, whom I co-supervised with Hasan, and this is part of her work. So actually what we worked in this is this is the crux of the whole paper, that it's a method to actually, it's a standard method to study virialized clusters, for example, Coma Cluster. And this is a cluster where you do not find any interacting galaxies. There are no interaction features, and hence you look for other kind of diagnostics to see the merger properties, essentially looking at the surface index as well as the Common diagram. So what we found for our sample is that for the majority of galaxies, the ones which have classical bulges, that's what we're defining what these things are. They have a bulge by total ratio greater than 0.3. Pseudo bulges are at less than 0.3. We also had the common relation, etc. And we found that for Coma cluster, the clusters will be by T greater than 0.3. Yeah, they must have formed by mergers, while those with less than 0.3 probably formed by several processes. This is the crux that I'm going to the details now. So essentially what we can we remove that bar, that zone bar, because all my titles will go. Okay. Yeah, this bar is. Yeah, okay. Because otherwise all my titles will go. So essentially what we are doing is we are quantifying galaxy morphology using various parameters, and I'll move this box also. I don't want this one. Yeah. So essentially we are quantifying galaxy morphology in this thing and using for this cluster of galaxies. There are various kinds of clusters of galaxies. The one that we are talking about is Coma Cluster, which is at a redshift of only 0.023. It has a distance of about 100 megaparsecs, and there are various features, reasons why Coma Cluster is an interesting cluster to study. I won't go into the details, but what we basically used was HST data, which is from the ACS Delhi survey, and essentially there were 25 regions which were observed by the camera with an exposure time of 1400 seconds in 2 bands. And oh god, this has gone down. Oh, this bar is creating a problem. So essentially, what we use the source extracted catalog from there. Yeah, what can we do about it? Oh, thank you so much. Thank you so much. Thanks. Thanks. Yeah. So essentially, for that, for the survey, we used the source extracted catalog which is available with it. And we found 219 objects which are stellarity index 0, which are galaxies basically. So these are the tiers, the 25 tiers, which describe the data set. Let's describe over here also. And so the first thing was membership. We do that using spectroscopic redshifts from various sources, which are mentioned over here. And along with that, we also, for the galaxy morphology study, we use GalFit. And what GalFit basically does is it decomposes the luminosity profiles of galaxies by fitting into various functions like Cersei profiles, biboculars, Gaussians, etc. And we did various fits for various things. So this is the Cersei profile. I'll run through this fast because we don't have much time, and I'm sure you can know. So here are some typical GalFit outputs. The basic advantage of this method is you have your science image, you create a model image using GalFit. The residual image is what actually gives out the features. For example, this galaxy, which is not very obvious to be a spiral galaxy, you can clearly see it over here. As well as if it has double cores or various other features, you'll be able to identify that using the GalFit outputs. So what we did is using for our sample, we segregated them into cluster members, non-members, the other redshifts. We also separated into the dwarfs and non-dwarfs, basically based on this criteria, absolute magnitude, less than -845, or these were the dwarfs, and we separated our sample. So finally, we had 132 members, of which 51 are non-dwarfs, 81 are dwarfs. Yeah, and these are the other details about this thing. So this is approximately the morphology distribution of the galaxies for our sample, and you can see the different morphological types. And these are basically done through visual inspection from the GalFit residual images, from which we actually classify the morphology of these galaxies. The other important parameter we got was the bulge total light ratio. So since what GalFit does, it separates it into the bulge component, the disk component, etc. We actually can find out these parameters for all the galaxies in our sample. And we could actually settle the ranges that we had for bulge to total per this thing for various morphological types for our sample. So it's plotted over here, the morphology distribution with the bulge by total ratio for, this is for the cluster members, for the non-members and the unknown redshift galaxies. We also try to correlate the morphology with the E by T ratio, which I showed you on the previous slide. We plotted the color magnitude diagram for these things. So you typically see that these are the members, which are different morphological types. They are mentioned over here. The red is ESO, SPO is pink, then you have yellow, and then the blue and green ones are the spiral galaxies, these ones which are over here. These guys are the dwarfs, these cyan ones. And the ones with crosses are the non-members. So you can see that this quite neatly occupies this region of the color magnitude diagram. And so here you can also see the B by T as a function of color, where you can see that larger B by T is essentially a redder in color. And we kind of look for these relationships. Right? And the other important parameter which we use from Galactic is the Sersic index. So when you fit the bulge to a Sersic profile, you get the Sersic index. And what we found is that the important factor is the factor of n greater than or less than 2. And that's basically an indicator of whether the bulge is a classical bulge or a pseudo bulge. And I'll come to why is that important. So we also did a morphology distribution of the Sersic index with respect to different morphological types and the B by T's, etc. So now this galaxy Sersic index for the dwarfs also when we did it, except for the 9 dwarfs, there were 9 dwarfs which are distinct. We had most of them boys. My mobile is not good. I have taken this. The other important diagnostic we used is what is called the complementary relationship, which is the relationship between the surface brightness of the galaxy, mu-e, and the effective radius. This is a very effective this thing again, which can be used for bulge types. So typically, when you make a plot of this surface brightness versus effective radius, you can see that these the ellipticals, the lenticules, etc., occupy this region within a 3 sigma width of this thing. While which basically indicates that these are what are called the classical bulges, which have Sersic index greater than 2. All these galaxies occupy this region, but like you can see the blue ones, which are the spiral galaxies, there are only 2 spiral galaxies in the sample. These ones are outside that, and they are the pseudo bulges. So in principle, both of these can be used as indicators of the bulge types. So we classify the bulge. What we are basically doing is we classify the bulge into classical bulges, which have n greater than 2 or n less than 2. Using the Sersic index as well as using the complementary relation, which I just showed you. And if you actually see, there's a clear morphology distribution with the Sersic index, which you can see. So So in the complementary diagram, I think this got repeated. In the complementary diagram, you can clearly see that the classical bulges are the ones which fall within this region, while the pseudo ones are the ones which are outside this region. So we found that for our sample, we confirm what kind of morphology types, and this is a detailed paper which has been published in MRRS. So this was the basis for the thing. So now I'll move to the main topic which we were talking about, is that the merger signatures. So then what we did is that for our members, for our dwarfs and non-dwarfs, in this case we did it specifically for the non-dwarf galaxies, 48 of them, we actually did the bulge decomposition. For dwarfs, we couldn't do it for both components. For this, we could do it for all. And we actually used that, got the B by T ratios, etc., and classified the bulges, right? So like I said, the classification of a bulge is a very important indicator of the merger history of these galaxies, right? So so classical bulges are a result of major mergers. This is an established thing, while pseudo bulges are basically indicators of secular evolution. So, sorry, yeah. So, so what we did is we classified our bulges in this way, and I'm sorry, but because I have only 2 minutes, you can clearly see that there's a relationship between the Sersic index of the bulge and the B by T ratio. It's like going like this, and the complementary relation also shows us which of our non-dwarf galaxies are classical. You can see a big chunk of them are classical, only a small number of them are pseudo, and essentially that's our basic result. That from our whole sample of these non-dwarf galaxies, 43 of them are classical bulges, 5 have pseudo bulges. And it's very important because here in this cluster, you do not see indicators of interactions in forms of, rings or streams, all that you have is the information which is sitting in the bulges. So if you can get it, so the only way you can get it is essentially through the bulge type, like I mentioned, which is got from both the methods, Circic index and this. You can also see that there's a relationship between the size, the center, distance from the center, and the color of the galaxies, as well as the thing. So I'll conclude with this, that the pseudo bulges that we see, the classical bulges are closer towards the center. They are within 4 megaparsecs of the center of the cluster. These are all classical bulges. While the pseudo bulges, they are at a larger distance away. These are the ones which have secular revolution between 0.62 to 1.1 megaparsec from the center. And so it's essentially, this is a good method to actually trace the merger history of a cluster, which is typically virialized in this case, where we do not have other indicators of this thing. So I think I'll end with this. Continue with this. And this paper has been published. This is in New Astronomy. The earlier one was in Monthly Notices. 2 more are still under review. Thank you.
Thank you, Priya. Yeah, progress.
Yeah. I'm here. I just want to ask where high potential or slightly greater than 0.3 as yeah, B by T greater than 0.3.
Yeah.
As classical pulse, do we have some strong?
Yeah, so there are some people who also have similar results, etc. So
Yeah,
the
but
references are there.
generally we think that the pulse should have a greater complement or a stronger complement, right? So is it 0.5 or 0.6 is the something?
Yeah, so that varies with different authors. You find it differently with different, it's like 0.3, 0.4, 0.5. But essentially, what you have is that the larger B by T's are the classical ones, and the smaller B by T's are the spiral types, which are the pseudo ones. But I think it varies with different authors, they are slightly different. Even we have also referred what we got is also slightly different from the others. But obviously, that's typical to the sample.
So, yeah, that's one question. And second question is, what is do you have an indication of the stellar mass of these galaxies? When you said dwarfs,
Yeah.
so interesting would be to see whether what are the masses of these dwarfs, and what kind of star formation rate would they have, whether they're quenched or still forming stars, or
Yeah, so actually that's the fourth paper is the one which is on dwarfs, in which we have done estimates of that trend. So that one is under review.
so what is
Long live India and France friendship.